All right, does anybody need more time to discuss these 6 with your small group members? I didn't hear too much talking. How about you take 30 seconds, discuss the answers that you came up with, your small group member came up with, see if you guys agree on them. Ionic or covalent? Formula units or molecules?
Formula unit is I guess not. Yep, I can't see it. Okay. I don't have my glasses.
Like half one, like they just come over. Like an iPad together.
All right, let's double check and see how we're doing on this. I'm going to be so happy to get a new computer next year. Oh, we got some pretty animals up there. All right, we are back. Now we're running here. So, somebody from group 1, ionic or covalent?
Ionic.
Okay, why is it ionic? Oh, both of them are non-metal, so they're on the same side of the periodic table?
Yeah.
They're both on the right side, so they're kind of in the same community, kind of cooperating with each other. So it's ionic. So they're like opposite charges.
Oh, no.
It has to be covalent. They're on the same side of the periodic table. They're working together, so it is covalent. All right, group C, group 2. Is this made up of molecules or formula units?
That is made up of molecules.
Good, because that's the definition of a molecule. A group of covalently bonded atoms. We just got done saying it was covalent, so it has to be molecules. Questions on that? All right, lab group 2, calcium fluoride. Ionic or covalent?
That is ionic.
Okay, what's the reasoning for that?
Because they're on separate sides.
Opposite sides of the periodic table, opposite charges. That is our definition of ionic. Good. C group 3, made up of molecules or formula units? Formula units, yep. Because we have ions, they're part of a larger crystal structure, so what's the smallest unit of that formula? By definition, it's a formula unit. All right, lab group 3. Number 3, P2S3.
Covalent.
It is covalent because P's and S's are on the same side. Made up of atoms, molecules or formula units. Team Lexi. Molecules. Good. H2S. We'll go with C group 5. Ionic. Okay, and why is it ionic? They are on opposite sides of the periodic table. What can you tell me about H, though? Is it a metal? Right, so this is the one element you really got to be careful with. H is on the left side of the periodic table, but that doesn't mean it's a metal. So you've got a non-metal, even though it's on the left side, non-metal, it is covalent. This is what happens when you hide an egg somewhere in your backyard and maybe you don't find it, and then months later you're mowing and then it cracks open. That rotten egg smell is from this hydrogen sulfide there, or dihydrogen monosulfide. So let's see here. Coal P, is it made up of molecules or formula units? It's made up of molecules. And then the lab group 6, what about number 5?
Ionic.
It is ionic. Okay, well, why? I thought N's, H's, P's, and O's were all nonmetals. When they're together, okay.
Oh, then wouldn't it be
Yeah, you would think so, but you were actually right the first time. This is a hard one. Why does it have to be ionic? If you just look at NH4, non-metal, they are covalently bonded. But together, you can't say it's a molecule because on the back of the periodic table, NH4 has what charge? Ammonium, the ion, has a +1 charge. So again, if you remember our definition of a polyatomic ion, it is an ion which makes up an ionic compound, ionically enough, but a polyatomic ion is bonded covalently. So it actually has both types of bonding happening. What makes the ion is covalent. These atoms are stuck together with covalent bonds, but because you have a charge, and because PO3 has a -3 charge, obviously if you have ions, it has to be ionic bonding. But what's sticking the P and 4 O's together is covalent bonding because it's a polyatomic ion. So overall, the entire compound would be an ionic compound, even though the polyatomic ions are made up of covalent bonds. That was the trickiest one out of the entire group there. Does that make sense? So you have polyatomic ions, which are made up of covalent bonds, but the polyatomic ions ionically bond with other polyatomic ions. All right, so what would be the smallest representative particle of this group? Lab group 1.
It would be. Oh, yeah, I'm looking at the wrong. Plutonium?
What?
P and the O.
No, but this whole thing is made up of molecules or formula units.
Oh. Formula units.
Right, because ionic bonding, by definition, is made up of formula units. All right, last one. C group 2, K2CO3.
That is definitely ionic.
Yes, and why is it definitely ionic?
Because it's not covalent. I don't know.
Okay, K is on what side of the periodic table?
The left.
Left side is definitely a metal. This is a polyatomic ion, so as soon as you hear the word ion, you should probably go with ionic, right? Now, even though CO3 is made up of covalent bonds in that polyatomic ion, the ions are bonded ionically. And lab group 2, made up of molecules or formula units? Formula units. Quick conversation in your small group. Why do we care so much whether a compound is ionic or covalent? Who cares?
That's how the reaction is.
You might want to think about your homework from last night. It is a little bit because they had the AC off over the weekend, and because it was so rainy last night, you could probably feel that stickiness. Yeah. All right, back as a whole group. Who cares whether something's ionic or molecular? Covalent. Aiden.
Because it depends on how the reaction is.
Okay, yeah, it depends on how what types of atoms are that make up. So that's how you figure out whether it's ionic or covalent. But why do we care so much? Why not just say it's a compound? Who cares if it's ionic or a covalent compound? Think about your notes from last week. Think about what you did with your homework last night. They have different properties. Ionic compounds have completely different properties than covalent compounds. Ionic have high melting points and boiling points. Covalent have relatively low melting points and boiling points. So if you know what type of compound it is, you can probably get a pretty good guess on what properties it has. Ionic compounds are probably what state of matter at room temperature. You think back to last unit when you looked at all those bottles that had ionic compounds in them, they were all what? Solids. Because they have high melting points and boiling points, room temperature, they're probably going to be solids. Whereas something like hydrogen sulfide, NF3, probably going to be what at room temperature? Maybe solids if they're really strongly attracted, but probably not. It's more likely to find them in what state of matter? Liquids or gases. Hydrogen sulfide is definitely a gas at room temperature. Water is a liquid at room temperature. Why? Because covalent intermolecular forces are not as sticky as ionic attractions between ions. Questions on that? Think about what you had to do for homework last night. What'd you do? You named compounds, correct? Do you name ionic compounds the same as covalent compounds? No, it's completely different. What do you use in an ionic compound to write the name correctly? Pardon? Yes, sometimes you use Roman numerals if there's more than one charge. Do you use any sort of prefixes in the names? No, because we look at charges to balance the formula. Can you look at charges for a covalent compound? No, there are no charges, right? They're not ions. So how do you know how many atoms are in a covalent formula? How do you know how many H's or S's, or how do you know how many P's and S's? Can you just say phosphorus sulfide? No, I could do that last unit. I could just say calcium fluoride. I know calcium is a +2, therefore I know I have to have 2 F's to balance the charges. You can't do that this unit. So what do you have to let the reader know? Maya?
How many of each?
Good, and what do we use to tell the reader how many there are? Prefixes. This would be diphosphorus trisulfide. The only similarity is that the second element is going to end in "ide," but that's really the only similarity. Questions on that? All right, so let's go ahead and move on then. So did we get them all right? Yep, formulas. Yep, we're good, good. Sweet, I love when my answer key matches the conversation. All right, so let's talk about chemical bonding. Next slide. You've already seen this slide before. It was from last unit when we introduced Lewis dot structures the last time. I always think it's helpful to kind of review it. So a bond could be formed when 2 atoms either exchange electrons or share electrons. Last unit, we were looking at swapping electrons. We had little arrows showing that electrons were being lost and another atom was stealing those electrons. We're not going to do that this unit. Why? Because they're not exchanging electrons. They're going to share those electrons. So last unit was about exchanging electrons. This unit is more like Mr. Rogers, PG appropriate, maybe even G appropriate. We're going to be sharing electrons. I know. And then Daniel Tiger came along and you thought
You ruined it. You ruined everything.
What?
You ruined everything.
Kids love Daniel Tiger.
What?
No, it's so annoying.
Okay.
It's nothing like Mr. Rogers.
It's his land of make believe. Right?
But Mr. Rogers is an idiot. That's the problem.
Right, because
Mr. Rogers was
he died.
Okay. It's still
Life goes on.
Same storyboard.
Okay,
I learned a lot today.
here we go.
I never knew, like,
Would you-
I never knew an argument over a cage show would happen.
It's beautiful. I tear up a little time every time I see Daniel
Have
Tiger.
you seen the movie from Mr. Rogers?
Yes. Okay, here we go. So atoms are trying to exchange electrons or share electrons so they get like an outer shell. Once they have a full outer shell, they can't take any more electrons. So most atoms are going to stop at 8 valence electrons. Remember, S gets 2 electrons, P gets 6, 6 plus 2 is 8. That's the reason why it's the magic number 8, because S and P orbitals fill up to get 8. Hydrogen and helium have to stop at 2 electrons. Would you agree they're the smallest elements on the periodic table? And they only have a 1s orbital? And how many electrons can you put in one orbital? 2, that's it. So hydrogen and helium will only ever get 2 electrons. Good review? Nothing new there? Right? Okay. So a single covalent bond, every time we draw a stick in our pictures today, that represents 2 electrons. One atom is sharing an electron, this atom sharing an electron. They bring their 2 electrons together. A bond is 2 electrons being shared. If we're going to draw a double line, that's 2 bonds, a double bond, that's the sharing of 4 electrons. Why? Because a single bond is 2 electrons. A double bond would be 4 electrons. No surprise, a triple bond would be how many electrons? 6. Every bond is 2 electrons. Questions on that? So, obviously we need to know how many valence electrons an atom has, so this is kind of review. We got to kind of brush off the cobwebs on this. before we can get to drawing any Lewis dot structures today. So quick show of fingers. How many valence electrons does hydrogen have? Be careful. Good, thanks for being respectful. Good. Column 1 on the periodic table, it has 1 valence electron. Good. Well, what about carbon? Quick show of fingers. Carbon has how many valence electrons? Good, I see a lot of 4s out there. S2P2, add them together, you get 4. Or you just simply say it's in column 14, last digit's 4, has to have 4 valence electrons. What about oxygen? It's got to have 6, it's in column 16, correct? Good. What about nitrogen? High 5, if you said 5, because it's in column 15. 2s2, 2p3, add them together, you get 5. And what about chlorine? Yeah, even though it's in row 3, it's still in column 17. Last digit is 7, 7 valence electrons. Good. What about calcium? Number 20. Yeah, it's in column 2 on the periodic table. That would be 4s2. And what about selenium? Good. It doesn't seem like we have too many cobwebs there. That would be 6. Questions on that? That's really going to be the first step of our Lewis dot structure. If you're going to draw dots, you have to know how many dots are present. Would you agree that's what we did last unit? Now, last unit, we actually took the time to draw those dots around those atoms. Those atoms were pretty possessive of those electrons. Now, because we're doing the whole Mr. Rogers, Daniel Tiger thing, we're just going to drop all those electrons in one big pot, kind of like a commune, and we're going to share all those electrons, okay? So we're just going to dump all those electrons in a big pot, and that's how many electrons we have to draw our picture. So what we're going to do is, let me just kind of give you a brief overview. We're going to do a Lewis dot structure in 1, 2, 3, 4, 5, 6, 7 easy steps. So anytime you have a question on how to do a Lewis dot structure, until you get the hang of it, I would go to step 1. When you're done with step 1, go to step 2. When you're done with step 2, go to 3, 4, 5, 6, 7. So what we're going to do is, I'm going to give you rule 1, and we'll do it for these 4 examples up here. Then we'll do row 2, or rule 2, and then we'll come back to our 4 examples. So we're going to bounce back and forth between the slides and slide 22. Now, if that would be easier for you to draw your pictures, I think it's way easier to draw on notebook paper. You can take the slide notes in your slideshow and just have a piece of notebook paper off to the side. And I think that's probably what I'm going to do. I'm just going to draw the 4 examples off to the side here. So my H2O picture will be up here. My CO2 picture will be over here. My PO4 3- picture will be there. And my C3H8 picture will be right there. Hopefully it won't get too busy on the screen. So step 1, we need to count the total number of valence electrons for each atom in the molecule. Let's do some examples first. So for H2S, how many valence electrons does an H get? 1. But if I have 2 H's, would you agree that would be 1 and 1? So I get 2 valence electrons for the H's. How many valence electrons does S get? Column 16? 6. 2 plus 6? 8 valence electrons. Close. 8. All right, let's do the same thing for HPO4 2-. Now, we're going to do the same thing. If it was a molecule, we wouldn't have a charge here. But then, because it's an anion, anions have extra negatives, we're going to have to add 2 negatives to the total. How many valence electrons for an H? 1. How many for a P? Column 15 would be 5. O gets how many valence electrons? 6, but 6 4s, 4 6s would be what? 6, 6, 6, and 6? 24? So normally we would stop there, but because I have an extra 2 negatives, I'm going to have to add 2 negatives to the total. Sometimes people want to subtract negatives, but keep in mind, we're counting electrons. If it's a -2, you have extra negatives. 2 extra negatives. Add that all up, you get what? 32 valence electrons. And if for some reason it would be a positive polyatomic ion, you're going to have to take away electrons. So N gets how many valence electrons? 5. H gets how many? 1. 4 of them would get a total of 4. That would be normally 9, but because it's positive, it lost a negative. Am I sure? Yeah, I'm positive. Okay, you lose a bad attitude, you now become positive. So I'm going to subtract 1. 9 minus 1 is 8 valence electrons. That's it. That's step 1. How many total dots are you dealing with? Questions on that? All right, so let me go ahead and clear my screen here. We're going to erase all this work, and let's go back to our 4 examples. Again, I'm going to be bouncing back and forth between my 4 examples in the 4 corners here. H gets how many valence electrons? 1, but I have 2 of them, so 1 and 1 would be 2. How many valence electrons for an O? 6. 6 plus 2 equals 8. All right, this will be a good time for a quick stretch break, just so we don't have to quarantine. So you want to move at least 6 feet away from the person that you are currently sitting with.
No, it's one.
All right, and we are back to our seats. All right, let's go top right-hand corner, CO2. C gets how many valence electrons? 4, because it's in column 14. O gets how many? 6, but I have 2 of them, so 6 and 6 would be 12. Is everyone comfortable with this? You're not going to be able to do a Lewis dot structure unless you can count atoms. Everyone good?
I like counting heads.
Sure, if you think heads are electrons.
That's what I think.
All right, cool. I wouldn't think of them as electrons, but that's all right. All right, C gets how many valence electrons? 4. 3 of them would be 12. H gets 1. If I have 8 of them, that's a total of how many? 8. For a total of 20. P gets how many? 5. O gets how many? 6 times 4? 24. What do I do with the negative 3? I'm going to add 3 electrons. Why? Because electrons are negative. For a total of 32. That's step 1. You have to know how many dots are in your picture. Ready for step 2? Let's do it. You're going to create the starting structure by using single bonds. Don't go crazy on me. You're not going to start putting double bonds and triple bonds wherever you want. You're going to start out with single bonds. A single bond counts as how many electrons? 2. So every time you draw a line, that counts as 2 dots. Usually, if it's not a carbon compound, usually the central atom will be the first atom. So whatever the formula says, whatever the first atom is, that'll usually be in the center of your molecule. If not, I'll probably give you some extra feedback on that. But H can't ever be at the center of your molecule. H can ever only form 1 bond. So you can't put H in the middle and connect everything else to it because you can only connect it to one thing. So usually the first atom is the central atom. Now, if it's an organic compound, lots of C's and H's, you're really not going to have a central atom. You're going to have kind of a chain of atoms. So you're going to form a carbon backbone. If there's 5 C's, you're going to connect the 5 C's kind of like train tracks kind of in a row, kind of like a backbone. So we have 2 different ways to connect these. Usually the first atom will be the central atom. If it's a bunch of carbons, we'll connect them in a chain. All right, shall we apply that set of notes? Let's do it. So which atom is going to be our central atom in H2O? Normally it would be the first atom, but can H be in the center? No. So I'm going to maybe put a little star over the O. That's my central atom. What type of bonds do we start out with? Single bonds. So here's a single bond to H. Here's a single bond to H. For now, I'm going to try to put those H's as far apart as possible. Later, when we get to molecular structure, we'll see that we're going to try to be a little bit more three-dimensional with it. All right, I wouldn't recommend this, but for right now, if you need to, how many dots does this line represent? 2. You could do this, but I think that gets a little messy. So eventually, you just need to see a stick as 2 dots, but if you need to draw those dots in there, go for it. All right, CO2, what's going to be our central atom? C. Z, senor. So we're going to put carbon in the middle. We're going to connect it to an O, connect it to an O. That's our starting structure. When you see C3H8, are you just going to put 1 carbon in the middle? No, you're going to form that carbon chain. So I'm going to connect the 3 C's. C, C, C. Using single bonds. And who's going to be at the center of PO4? The P. And I'm going to connect that P to 4 O's. So single bond O, single bond O, single bond O, single bond O. Did I lose anybody? We're good? Great. All right, rule number, yes. So you might not at this point know how do you put those H's on. Do you put all 8 H's on the left C? Do you put them on the middle C? Do you split them up? At this point, you probably need maybe 1 or 2 more rules to know how to split them up. You're going to want to probably split them up evenly, but unless you know like the next rule or 2, you might not know how to put those H's on there. So we'll get there. All right, now we want to follow the octet rule, which means 8 valence electrons. We're going to put those dots on the outer atoms first, and we'll work our way in towards the center. Now, keep in mind, hydrogen is such a small atom, it'll never get 8 dots. As soon as you draw a single line sticking out of H, you don't do anything else to H. Anything else you would do to H would be marked wrong. H only ever gets a single line. All right, would you agree if you take a look at this picture up here, we're supposed to have 8 electrons. But this picture only has 2 and 2, which would be 4. I'm missing some dots, correct? I have to draw 4 more dots up there. Am I going to draw them around the H's? No, as soon as H gets a single bond, you're done. So where am I going to put those dots? On the O. And when I do that, would you agree there's 2, 4, 6, 8 electrons surrounding the oxygen? Yes, that sounds like an octet to me, right? 8. We're done with that picture. We probably don't even need the other rules to figure out that picture. All right, let's try for CO2. Would you agree I already have 2, 4 electrons in this picture? 2 and 2 is 4. I have 12 more dots to draw up here. Do I start on the center or start on the outside? Start on the outside, right? The outside atoms get the octet first. If this is 2 electrons, would you agree I need 3, 4, 5, 6, 7, 8? That's 8. If this is 2, I need 3, 4, 5, 6, 7, 8. I'm done. I've used up 8 and 8. That's 16 electrons. Right? Now you might see, does carbon have 8 electrons surrounding it? No, that only has 4. So on the next slide, we'll see that maybe carbon's not so happy. So maybe we can put like a little frowny face there. We'll fix carbon on the next slide or 2. But at this point, we're out of dots. You don't get to be an electron magnet fairy. You can't just like throw electrons up there wherever you want. If it says you get 16 dots, that's all the dots you get. All right, now let's take a look up here. Now, technically, up here we've been adding dots, but would you agree we have some more H's, just like Brendan said? We have some more H's up here that need to go up here, so we're going to have to use some more electrons to draw some dots. So if this carbon has 2 electrons, how many more electrons does it need to get to 8? 6. That would represent how many bonds? 2, 4, 6, 3 bonds. So I need 3 more bonds worth of electrons, and they're going to be bonded to H's. This carbon in the middle already has 2 bonds, which is 4 electrons. How many more total electrons does it need to get to 8? 4 electrons, which is how many bonds? 2. We're going to use those bonds to connect to those H's. The last carbon has 1 bond. To get to 8, it needs 3 more bonds or 6 electrons. So that's how you know where the H's are connected. And real quick, we want to make sure that we haven't like created magical electrons up here. Would you agree this picture gets 20 electrons? And if I look, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, that's my 20 dots. Do I have 3 C's? Yes. Do I have 8 H's? 1, 2, 3, 4, 5, 6, 7, 8. We're done. That's a good picture. That's propane. Anybody grill out this weekend? Turn on the propane gas grill. That would be the molecule you were burning.
Awesome.
All right, let's take a look over here. Would you agree oxygen it only has 2 electrons right now? We need to get it to a total of how many? 8, all right? Because that's the octet rule. So each one of these O's needs 1, 2, 3, 4, 5, 6 more dots. It's kind of fun listening to you take a covalent compound test because I just hear a bunch of the entire time. You're just drawing dots, right? Questions on the octet rule. So step 1, count the total number of dots. Step 2, connect the atoms with single bonds. Step 3, make sure you've used up all of your dots by meeting and satisfying the octet rule, except for H. Ready for step 4? Let's do it. Recount the total number of electrons. Well, we kind of already did that. Place leftover electrons on the central atom. If you run out of dots but need to meet the octet rule, you might have to break out a double bond or let's say a triple bond. So 8 valence electrons, 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. This is a good picture. We need 16 electrons up here. 2, 4, 6, 8. 10, 12, 14, 16. Octet, 2, 4, 6, 8. Octet, 2, 4, 6, 8. Octet, 2, 4. No, we're going to have to fix this a little bit, right? We're out of dots, but carbon isn't surrounded by 8. Would you agree there's some dots up here we could move into an extra bond? It doesn't matter which set of dots you move. I'm just going to move this pair of dots, and I'm going to use that to create an extra bond. Does oxygen still have 2, 4, 6, 8? Yes, but now that carbon has how many? 2, 4, 6. It's better, but is it perfect? No. So I need to move one more pair of electrons to get carbon 2, 4, 6, 8, correct? So do I want to go from the left side again and have like an uneven triple bond, single bond, or do I want to try to even things out? Yeah, we're going to even things out. So I'm going to move another pair of dots. It doesn't matter which pair. I'm just going to move this pair, and I'm going to create another bond. Now, do you go crazy and keep doing that? No, every time you stop and double check. Do I have 16 electrons? 2, 4, 6, 8, 10, 12, 14, 16. Check. Do I have 8? 2, 4, 6, 8. Yes. 2, 4, 6, 8. Yes. 2, 4, 6, 8. Everybody's satisfied with an octet. You're done with that picture. Sometimes people go crazy on it. Last year we did this with sidewalk chalk on sidewalks in people's driveways because it was quarantine. Why not? So we had our lesson outside and we drew all these pictures on the sidewalk. Got some strange looks from people walking their dogs, but it was awesome. We had like chemistry all over limits. All right, let's take a look at this picture. 20 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm out of dots. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everyone's happy with an octet. H will only ever get one line. The last picture up here. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 8, 8, 8, 8, 32? I need 32 dots. Phosphorus, 2, 4, 6, 8? Yes, we're done. So think what we've done so far. We counted total number of dots. We connected the atoms with single bonds. We met the octet rule by putting the extra dots around. And if that didn't fix our picture, we had to kind of move some of those dots into a double bond, a triple bond, or maybe 2 double bonds. That's 4 steps. We're almost done. Step 5, determine the formal charge for each atom. This determines whether your picture is as good as possible. So this would be a charge of -1, 1 minus. What does a formal charge look like? Put on a tuxedo. Now you're formal. That would be -1. So I said in the past, I wasn't gonna take off whether you wrote a 1 minus or a 1 minus or a -1. Because for most people, they're like, well, that's the same thing. Technically, a 1 minus is a real charge. That's like the charge of an ion. Whereas this idea of formal charge, we're kind of coming up with some like mathematical calculations to kind of calculate a charge, but it's not really a real charge. It just helps us determine whether our picture is as good as possible. So with that being said, that's pretty much going to wrap things up for today. We won't be able to finish our pictures, but you can at least get through the first 4 steps. So we're going to have to finish step 5, 6, and 7 tomorrow. So in this molecular modeling packet, there are 12 pictures. I want you to go through steps 1 through 4 for these 12 pictures. Now this, I would say, would be your final draft. I would probably put those on notebook paper so that you get to work out all the bugs on notebook paper, and then finally you can copy all your final answers in here. So we're going to do a lot of fixing of these answers tomorrow. But you're going to do the 12 pictures, just steps 1, 2, 3, and 4. I'd probably use pencil versus pen. Because a lot of times people have to fix things, so we work out all the bugs. So I know right now Google Calendar says you have to do all 12 pictures, all steps 1 through 8. But right now we only have the first 4 steps. So that's half of your picture. You can pretty much ignore page 1. That's just some review if you want it. So starting on page 2, you have 12 pictures. And again, you're only doing steps 1, 2, 3, and 4. Counting atoms, drawing single bonds, recounting electrons, putting extra electrons starting around the outside, working your way in towards the middle. All right, nice job, guys.